In this morning's first parallel session is by Tony Colaprete on a model for the distribution of volatiles at the L-Cross impact site. Tony?
Thank you, Ross.
Take it away.
Thank you, and I'll speak loud as well. People migrate out. I apologize for those who were in Houston a few weeks ago. You're going to see a repeat. I did change a few figures, so it's not entirely the same. A little shorter, and hopefully I can get through it more clearly. Certainly want to point out that I've got a number of colleagues working on this with me. What I wanted to do here is start the discussion and the synthesis of basically a lot of what we saw in the L-Cross data. And I'm just going to talk about the L-Cross observations, but really the synthesis includes all the data sets. And earlier in this meeting, you heard Mike Wargo refer to synthesizing all the data sets together that we're getting from all the various missions, and that's really critical. Obviously, to understanding this very complex and marvelous moon we have. So what I'm going to do, though, is try to focus on one place, the L-Cross impact site, and take the data from the L-Cross observations in the kind of the context of what we understand in terms of its environment, the L-Cross impact site environment, that is, the distribution of hydrogen and temperature and so on, along with what was observed as a function of time. And you heard earlier talked by Brendan about how there were these two impact plumes. That's really critical for us to understand. I'm going to comment on that because if we look at these things, if we look at the data as a function of time, there is some hope that we can actually squeeze out a little bit of information about the distribution with depth of some of the things we saw. But more so, I think, when you consider the neutron data and some of the analysis that Rick Elphick and his colleagues have done on reconciling concentrations of hydrogen with the neutron data sets, we can, I think, start to begin to understand the real heterogeneity, the spatial lateral distribution as well. And I think that's really important to understand the processes, of course. And you saw in the MCube data how the spatial distribution is so complex and marvelous. I think, likewise, it's going to be similar at the poles with the different forms of volatiles, hydrogen-bearing volatiles we may see there. So, that's what the purpose of this talk is, and first we start with the site itself, and I won't dwell too long on this except to say, well, we hit some place really cold. As you heard earlier, the diviner temperatures put our impact site at about 40 Kelvin. It's one of the colder places in the Cabeus region and in the South Pole in general. There is a very significant neutron depression there, both in the Lunar Prospector and the LEN data. One place they agree very, very well is that Cabeus has a lot of hydrogen, and this is one of the primary reasons we impacted there. The topography is very interesting there too, and I think this is an important place where we can really look at with the new LOLA data set as it gets higher and higher resolution, more and more points in the polar regions. Are there correlations? You saw some correlations, broadly speaking, with slopes in the LEN data, but what does that really mean in finer scales? Are there things we need to be interested in? And I'm going to talk about that because I think that's important. The L-Cross observations, I'm really sorry that for those of you who've seen this figure about 1 million times, but it is a roadmap for the L-Cross impact event. And really what you'll see in here in a second is it is describing the event in terms of the two plumes that came up, the material and the timing of that material. And so if we can tie it to this, we can kind of unravel what happened. This shows the radiance, actually. This figure shows radiance as a function of time relative to impact. And what I've highlighted here is the first impact period. And I'm going to talk about 3 different periods. What I call the flash period, which is the first really second of flash and then the quick rise of the ejected into sunlight. That's this peak here. And then the next period is the curtain period, and that's what I call it, and that's where we basically have reached our peak curtain brightness and we trail off. And this was mentioned yesterday that we don't actually trail off to zero, back to zero, that there's this long-lasting kind of trailing brightness that goes on for the 4 minutes. And then lastly, we dip into this is the final seconds really of the mission where the observation spacecraft is dipping into the curtain and into the darkness of Cabeus. And that's how I'm going to divide each of the observation sets I'm going to talk about next here. So the first period, the impact plus 3 seconds, was really interesting. This was the first indication that we had hit something really interesting in that the flash was very different than what you'd expect from a normal normal impact. Now, we've measured flashes from spacecraft before. Japanese spacecraft Hitran a while back, and Smart 1 spacecraft, that flash was observed. So we have some sense of what, at least spacecraft, not Centaur rockets, so that's different, as you know, but we have some sense of what the flashes should look like. We built an instrument to detect that type of a flash. We had another near-infrared instrument working to monitor that flash. And what we found was that the flash was incredibly subdued. The luminescence efficiency, the efficiency from going to the heat to visible, the impact heating to visible light was tremendously low, 10 to the minus 5 or less. And also, so we didn't see a visible flash at all. Now that could be because the flash was actually obscured by this high-angle plume you might have heard about yesterday from Brendan, but it's also because it could have been completely subdued because of the low temperatures and impact, as well as a volatile phase change. We did see it in the thermal infrared, or near infrared, I should say, and that's what this figure shows here. This is relative or total radiance just integrated across the near-infrared spectrometer as a function of time. We're in a flash mode here, so we're only sampling very coarsely, but very quickly. And this shows the rise in the flash. And what's very interesting is the breadth of the rise, how slowly it rises and then decays. And Sandy Davis here at Ames and Pete Schultz has looked at this. This is really indicative of some very porous, 70%, this was what we reported in Pete's paper in Science, 70% porosity where we impacted. Shortly after that, then, that impact, we were taking visible spectrum, and the visible spectrum had long integration times to be sure we got enough signal to noise, and that's what's shown over here is the radiance as a function of wavelength in our ultraviolet visible spectrometer. This red line spans the actual impact point that we get from the near-infrared flash time and the timing of the trajectory on the spacecraft. So the actual impact occurred, but you don't see any real brightening here. There's, like, as I mentioned, there's almost no visible light coming from it. But you do start to see some emission lines jumping up immediately with impact. Just a second or so later, or less, in the next integration period, you start to see the continuum rise up and show clear. This is a solar spectrum up here for reference. You start to see the sunlight scattering off the ejecta cloud dust. That's the most immediate and direct an easy way for me to understand how fast some of this ejecta was going, as it went from basically nothing to getting into sunlight in less than a second, and the altitude to sunlight was about 830 meters, so this really shows the ejecta was moving up. Some of it was moving quite fast, up to probably 800 to a kilometer, 800 meters to a kilometer per second. And you see these strong emission lines here. Sodium is very nicely shown right here. You see some other emission lines throughout. These are some of the preliminary identifications Pete made in his science paper. And we can map those, and Rosemary Killian observed these from the ground, has a very nice paper on it that shows that once we impacted, a lot of this sodium, a lot of these emission lines were coming from species that came up with the dirt. And that's an important point. We don't see these sodium lines immediately. The thermal impulse from the impact was not enough to release large amounts of very hot vapor immediately. In terms of these emission lines, what we saw was the sodium and some of the other emission lines coming up with the dirt and then beginning to fluoresce shortly afterwards. So the gases were either, as cold, are only moving 800 meters per second as well, or they're actually entrained in some of the grains in ICU matrices or whatever, some combination, and only started to fluoresce as the material came up. After that period, then we had this broadening of the ejecta curtain. It was brightest about 20 seconds. Two figures here. This shows the ejecta curtain is about 10 kilometers across at 20 seconds. This is Cabeus crater. This shows, again, a couple things. It shows the brightness as a function of time and the color. Jen Hellman made this figure. Basically, it shows what I showed in one of my very first slides. The hollow square shows the brightness of the visible spectrometer. And the colored dots, though, show the blue to red ratio, where she's looked at the 350 to 400 nanometer over the 550 to 650 nanometer wavelengths. And you see this bluing very early on, and it's quite significant. And then it trails off, doesn't quite ever get to what it was pre-impact, and then might spike up again towards the end. These are some really important, this is an important figure in terms of understanding what really happened in terms of the two plumes. And I like to call this a tale of two plumes. You heard about how because we had a hollow projectile, it created these two plumes. Early on, we had this spike as a combination of both a low angle and a high angle plume of very fine particulates. That's why we had this bluing. And these particulates had to be submicron to get the kind of bluing we're seeing. And then that trails off to this long, persistent high angle plume seen here. This is a little cartoon that I've made here showing these two different angular plumes that describe basically what we're seeing. And right now we're working hard to really detangle this. Why this is important for the rest of my talk is this high angle plume, as you heard, had the highest velocity and was probably excavating material very near the surface, within the meter or so, maybe 2 meters of the surface, where the lower angle plume was probably excavating deeper, but was shorter lived. In this early period, we saw our first signs of water ice. There's some of the continuum here, but this is the very early on is when we saw the brightest, strongest near-infrared signatures, because basically the dust just fell out and we only had the background scatter of the crater below us as a source. But we saw some pretty clear indications of water ice early on, and we were able to map the water vapor band out here, which actually became more distinct as we got further into this period, this temporal period here. And that's what I'm showing here. So the point here is there's this continued evolution of ice and water vapor and other volatiles throughout this early period. Data that I'm working on right now is from the near-infrared spectrometer that was looking at the sun. We had a near-infrared spectrometer that was watching the sun as we descended, as well as the one looking down. And so it was looking for any kind of material that was occulted by this, occulting the sunlight. Had very high signal to noise, you had the sun, and so we could measure very small signals. This shows the reflectance minus an average reflectance as a function of wavelength here from our solar viewing near-infrared spectrometer. What I did was I basically made a reference spectrum just prior to some time period, and then differenced later spectrum from it. And you can see this black curve is basically corresponds to an altitude above the surface of our observing spacecraft of 46 kilometers. And as we dip into the shadows deeper and deeper with our spacecraft, you see that reference, our difference from that reference spectrum increases and increases. You get these nice features through here. This is a fit that I've done, preliminary fit here showing you can do most of the fitting with just water ice and water vapor. However, there are some strong bands out here that are requiring some other species to be fit. Here, this is a C2H4 that actually produces a pretty good fit at longer wavelengths. So we see these clear water ice grains much later, 4 minutes after impact. That means they're, thanks, Dan. That means they're relatively clean and pure. It is not dirt with a veneer of ice on it. That would sublime within a minute or two. This is much more like granular ice, I think, that we're seeing as it falls down. So possible models. I'll go through this quickly. Dry highlands like regolith? No, I don't think so. Lateral homogeneous. Very early on, I was saying, well, L-Cross will test whether or not it's smooth peanut butter versus chunk of peanut butter. My kids loved it. A lot of people thought it was just kind of silly. But that's really the two models I think we can test possibly with this is the hydrogen that we impacted into smooth, laterally homogeneous, or is it heterogeneous? And right now, based on the modeling, as I mentioned from Rick Elphick, to get the kind of heterogeneity, or to be consistent with the neutron data sets, you need some kind of heterogeneity if the L-Cross data is at all representative of the actual water ice concentrations there. So I think this model here, lateral heterogeneity with a lot of other volatiles, is the most consistent. I won't read through these. These you can read through yourself, but this basically summarizes what I've just been describing, the various observations and the possible implications. And from these, we can build a possible model for the L-Cross impact site where we have this frosty layer up top that has a lot of bound or entrained light metals, volatiles, frothy stuff that at impact was released very quickly. This is what LAMP saw. This is what we saw. A lot of these species coming up very quickly. And then the high angle plume was definitely excavating through that and into this more ice-rich sublayer down to a meter or so. Then the lower angle plume and the lower earlier ice signatures were possibly from a deeper reservoir of water ice. So that's basically what I've just said here. And one of the interesting last points that I'll make, I think, is based again on the work that Rick and others have done. And looking at this near-infrared image of the L-Cross impact site, I think topography may have a lot to do with it. If Rick's conclusions is that you need about 40 or 60% heterogeneity to be consistent with the neutron data sets, then it could be that, you know, these double shadowed regions, which I'm showing here, these regions inside this is a near infrared image. The sun is actually up here to the upper left, but you can see in these craters, the actual illumination source is from scattered light on the opposite side of Cabeus. And so these regions here are basically double shadowed inside of Cabeus, meaning they are not getting a lot of scatter light, at least this time period, as well as sunlight. So that's an easy study I think you can take on with the LOLA data and diviner data to really look for this kind of fractional coverage of these double shadow regions within the PSRs and see if that matters. And with that, thank you.
Thank you, Tony. We don't have time, but we'll take precisely one question. Does anybody have one question? Oh, it's not your fault. I blame Botkey for letting the first session go over. Mike?
Tony, about the lateral, excuse me, lateral heterogeneity versus vertical heterogeneity. And this may be a better question for Rick, but is there a way to distribute the water vertically such that it can be made consistent with the natural length scales associated with the neutron measurements as well as the measurements that you've made?
Sure, anything can be done.
Yeah, yeah. And my so experience with Rick is it's an unbound problem in a lot of ways.
And that's really what I was getting to. That the lateral heterogeneity proposal, you would have to bring additional stuff to the table to increase your confidence level in it. Is that a fair way of saying it?
Yes, and what we're bringing to the table here is, again, this is why it's so important to really get as best as we can a feel for what we excavated into, how deep we excavated into. The neutron spectrometer is sensitive to about 70 centimeters or so. We excavated that top meter, it looks like, and so you have to make that assumption is how are we distributed through that top meter? It's going to be almost impossible for us to really tell that at this point. But if you took the kind of concentrations we saw in our dust plume and used the neutron data set, it requires, I think, some extraordinary burial is one way to do it, or this heterogeneity. And Rick, you can maybe comment.